apply to calculate an integral. Okay, and today I'm going to show you again also how to get the coefficients. We've seen yesterday how to get the partial fractions decomposition without calculating the coefficients. Today we'll see how to find them. Okay, and in the first example we have the integral of 1 over x cubed plus x to solve. And you guys notice here this is a polynomial function of degree 0, and this is a polynomial function of degree 3. It means the two conditions are satisfied, the condition that we've seen yesterday. And you have always to verify if the two conditions are satisfied. Otherwise, if the second one is unsatisfied, you need to use the long division that we've seen yesterday. All right, so let's get out here and see how to solve this one. We want to calculate this integral, as I told you, and to use the partial fractions decomposition we've seen yesterday. The first step consists, to factorize the denominator, and when you do so, you guys will get x times x squared plus 1, and this is a linear factor, and this is a quadratic factor, and it's irreducible. As you can see, we cannot factorize it. That's the meaning of irreducible. And when we go to the second step of the partial fractions technique and focusing on the linear factor, is going to be the denominator, and numerator going to be a constant a. As I told you yesterday, you can use a, b, c, whatever you want, or a0, a1, a2. I just use a over x. And from the second one here, since it's not repeated, it's going to be just bx plus c over x squared plus 1. And this is, exactly what we did yesterday. And in order to calculate this integral, we need first to find the values of a, b, and c. Okay? And to find those values, we have just, to calculate the common denominator here. So we just recompose, these two fractions. And to do so, you multiply here this denominator up and down, and this denominator up and down in order to get the common denominator. And that's what I did here. So we'll get ax squared plus 1 plus x times bx plus c. So we're going to expand, the numerator and the denominator. So when you expand it here, you will get exactly this numerator here, and the denominator still equal to the initial one, because it was just obtained from there. And now I'm gonna rearrange the whole thing here, keeping all terms containing x squared together. So you guys can see the coefficient of x squared are a and b. So we can write it as a plus b times x squared when we factor out the x squared, and we'll get cx plus a. And now we have to compare, the equation that we have on the left and the equation on the right, because they are equal. And to be equal here, since the denominators are the same, it means the numerators should be the same. And this numerator a plus b x squared plus cx plus a should be equal to 1. And the only way to get the two numerators equal is to compare term by term. So for example, here, if you take the first term and check, the coefficient of x squared, and you check here, what is the coefficient of x squared? It is 0 because x squared is missing. So it means to be equal, a plus b should be 0. C also should be 0 because there is no x here. If there is no x, it's because its coefficient is 0. And a, b equal to 0, c equal to 0, a equal to 1, because we have 1 here. And that's exactly what we got here. A plus b should be equal to 0 because the coefficient of x squared from the left is 0. The coefficient of x from the left is also 0, so the c should be 0, and a should be equal to 1. And knowing the value of A, I'm going to substitute in the first equation in order to get the value of B. So A equal to -1, equal to 1, sorry, and it means B equal to -1. And knowing the values of A, B, and C, I'm gonna go back to this step and substitute, A, B, and C by their values. And by doing so, this becomes 1 over X, and here you get, -1 X, and C is 0. And now we're ready to calculate the integral. Any question before I move to the next page? All good? Okay, so if you don't answer to me, it means, that's fine.
Excuse me, sir. What did you say is the reason why A is equal to 1?
Because the coefficient here, there is no X here, is a constant, is this here, the 1.
Thank you.
Okay, so this numerator, so you guys have this. From this equality here, so it means to be equal, numerator 1 should be equal to A plus B X u squared. Okay, and plus CX plus A. This is C. And you see this one, this means 0 times x squared. Because you don't have x squared, it means its coefficient is 0. That's why you don't have here x squared. It's only 1 plus 0x plus 1 equal to this. Okay, so if you check, the coefficient, it means this coefficient here should be equal to 0, the coefficient of x squared, and the coefficient of x is 0 from the left, and this is a constant, and the constant from the right is A, so it means A should be equal to this one. Is it okay?
Yeah, it's okay. Thank you.
Well, so next I just substitute, here I substitute, A by its value as I told you. A was equal to 1, going to be just 1 over X. And this is my B equal to -1 and plus 0. I didn't write it because C is 0. Is it okay? So back to the previous page. So from here, I just substitute here X by 1. That's what we got here. And you substitute B by -1, it becomes a minus X, and C is 0. So it means this term becomes a minus X over X squared plus 1. And that's exactly what I got. Okay, the C is 0 here. Now, this was our initial integral. So since I already, show the find the partial fraction, so it means calculate this integral, going to be exactly calculating this integral. And you notice here, the antiderivative of 1 over x is ln of 1 over x, ln of absolute value of x, sorry. And for the second term, you guys can see the numerator is almost equal to the denominator. Just want to write it down. Here's a different step. Maybe you guys can notice exactly what happened here. So you have integral of x over x u squared plus 1. Okay, just from here. I just want to show you why it is equal to this. But what I notice is, if you calculate the derivative of this denominator, you guys will get 2x, but the 2 is missing. So it means this is just equal to 2 times is equal to 2x. I multiply the numerator by 2 and the denominator also by 2. All right, so why I multiply here by 2? Because I know if I calculate the derivative of the denominator, I'll get 2x, and I'm trying to get something like that. I'm trying to get integral of f dash over f, right? And you guys know this is equal to ln of f plus a constant c. Since I know my denominator is 2x squared plus 1, and I realize if I differentiate it, I'll get 2x, but here the 2 is missing. It's not a big deal, so that's why I just want to get the 2, and to get the 2, I have to multiply 2 up and down. And then this becomes, I'm going to take this 2 out from the denominator. It's going to be 1 over 2 integral of 2x over x, you square it. Is it okay? And you guys know now we have exactly this form. Integral of f dash over f. And f dash over f by chain rule is obtained from the derivative of ln of f. Okay? This is equal to, because you've seen this in 1500, because the derivative of ln of f is equal to f dash over f. That's why. So since the derivative of ln of f is equal to f dash over f, it means the integral of f dash over f is equal to ln of f. And that's exactly what I have here. So it means this is equal to 1 by 2 ln of, but absolute value of x squared plus 1. But x squared plus 1 is always positive. That's why I don't need the absolute value. I can drop the absolute value because it's already positive. And plus the constant c, for example. And this is exactly what I did to get this part, the second term here. Is it okay? And now my constant, I call it d instead of c. Why? Because, you know, initially I use c as a coefficient, and if I use a c again, it could be confusing because we already found c equal to 0. We don't want to use it again. We have to change the name. So the constant now is called capital D. But doesn't matter how you call your constant. This does not change anything. You can use whatever you want as the name of your of the constant. Okay, make sure you guys understand this part because we're gonna use this this kind of integral many times today. So because we'll get something like that, always integrating f dash over f. Any question?
No, sir.
All right, so can I erase this? All right. All right. So next example. So second example, we just want to integrate now x over x to the power 4 plus 7x squared plus 6. And yesterday we already seen, this partial fraction decomposition. I will not repeat it again because we did it yesterday in example 7. But now we want to calculate the integral. Okay. All right, so that's why I just want to remind here the formula that we've seen yesterday, according to example 7 that we've seen yesterday in question 3. We already proved, the partial fractions decomposition is equal to this partial fraction. I'm just gonna go back there and show you again. We don't want to repeat it. It's right here. We did it yesterday. Okay. It's the same rational function, but today we're gonna integrate it. And to do so, we need to find, the coefficients A, B, C, and D. If you look at your notes, you already have it. So since I already have the partial fraction decomposition now, next step is to find these coefficients, and then we will integrate our function now. Okay, and we're going to repeat the same thing, same technique to find the coefficients. You have just to recompose this sum, and by finding, the common denominator. And when we do so, we'll get exactly this. You multiply up and down. I'm going to let you write down if you guys don't have it so far. Are you done with this, the partial fractions decomposition? All good?
Yes.
Now, if you calculate the common denominator, so you have to multiply the first numerator with the second denominator and the second numerator with the first denominator. And we expand it. Okay, so when you expand the denominator, you get the same thing. And here, when you expand it here, we've got ax cubed plus 6ax plus bx squared plus 6b. And from the second term, so it's going to be cx cubed plus dx u squared plus cx plus d. Now I'm gonna keep together all coefficients of x cubed, all coefficient of x squared together, the coefficient of x together, and the constant together. So you guys can see here for x cubed, the coefficients are a and c. And when you factor out the x cubed, it becomes a plus c times x cubed. And for the coefficient of b of x squared, so we have b and d. So that's how we'll get b plus d times x squared. And for the coefficient of x, we have 6a, and the next one is cx. So we'll get just ca plus c, 6a plus c. And for the constant without x, we have only 6b and d. That's exactly what we have here as the last term. Okay, now you guys can see the denominator is still equal to the same. We have only to compare the two numerators. And you can check here that the coefficient of x cubed from the right is equal to a plus c. And from the left, the coefficient of x cubed is 0 because there is no x cubed here. If one coefficient is if one x to the power n is missing, it means its coefficient is 0. That's why. So that's why here a plus c should be equal to 0, b plus d equal to 0, 6a plus c should be equal to 1 because the coefficient of x here from the left is 1. And the constant 6b plus d should be equal to 0 because there is no constant from the left as the numerator. Now you guys have here now a linear system of 4 equations with 4 unknown. I'm just going to use the basic method, the easiest one, which is the substitution one that you guys have all seen in algebra. I'm going to just express c in terms of a from the first equation, so you get just c equal to negative a, and from the second equation I'm gonna express d in terms of b, so it's going to be just d equal to negative b. Okay, and in the third equation I'm going to substitute c by its value in terms of a. So you guys can see here what I did is take this c and substitute in the third equation. I substitute here, right? So when you substitute c by its value, it becomes 6a minus a because c equal to negative a. And we'll get here 5a equal to 1. So that's why a gonna be 1 by 5. And knowing the value of a, you guys can substitute here a by its value in order to get the value of c. Is okay? All right. Now we're just going to change the color. Now from this equation here, we express d in terms of b, and we substitute in the fourth equation. We substitute here d by its value. And now this equation becomes 6b minus b equal to 0. It means 5b equal to 0. And this is obtained only when b equal to 0. And knowing the value of b, you substitute here b by its value in order to get d. So that's why d is going to be 0. Any question? All right. So now knowing the coefficients a, b, c, and d, we're gonna substitute these coefficients by their values in the partial fractions. Now I'm gonna substitute here. What I did here, I just substitute a by its value. Okay, and b is 0, c is equal to -1, and d is 0. It was here, so in fact it's gonna be here plus 0. Because this is your a. it was ax plus b. This is a and b is 0. And this is c, which is equal to negative 1 by 5 plus d, and d is 0. And this is was, what we got from the partial fractions decomposition. I just substitute again here. Okay. And this is equal to 1 by 5 times x over x squared plus 1 by 5 x times x over x. So here going to be square. Oops. Oh. Okay, so we just substitute. So now we're ready to calculate the integral. Is there any question before I move to the next page and calculate the integral? Any question? So you guys are done with this page?
Not yet.
Not yet?
Yeah.
Okay, I'm gonna let you write down. So let me know whenever you're done.
I'm done.
All right. Okay, we finish this one. No, is it here? That's not this one. We're gonna go to okay. So we did this. All right, so now we're gonna integrate because we substitute here. So we integrate, so 1 by 5 is a common factor, so that's why when we apply the integral, I'm gonna take it out the integral. So we'll get just 1 over 5 integral of x over x squared plus 1 minus x over x squared plus 6. Okay, and we already proved this. It's the same as the one that we did in the previous example. It's going to be 1 by 2 ln of x squared plus 1. And I already show you, how this part was obtained. And it is similar to this one, because when you integrate this, you guys can see the numerator is almost equal to the derivative of the denominator, because here it shows if you differentiate the denominator, you will get 2x. So the 2 is missing. That's why we divide by 2. And we already have, as I told you, we have this form integral of f dash over f. That's what we have in both situations. And we know this is equal to ln of f. So here, that's exactly what we have. And this case too. But the reason why we divide by 2 is the 2 is missing here on the top. So that's why. So if you integrate differentiate this function, you will get 2x over this, and the 2 cancel out. And I'm gonna drop the brackets here. And I add the constant c. The reason is I used previously, c. So that's why I cannot use it again here as the constant. Okay, because we already found c equal to -1 over 2, 1 over 5, sorry. And if I drop the brackets, it's going to be 1 over 10 ln of x squared plus 1 minus 1 over 10 when you drop this bracket. We multiply by 1 over 5. Any question? Any question?
No, sir.
So you guys are done before I move to the next example, number 3. All right. Third example, we just want to integrate this rational function again, and you guys can see for the third example, the 2 conditions are satisfied. It means we can use the partial fractions technique. So you see the numerator is a polynomial function, same for the denominator, and the second condition is also satisfied because the degree of the numerator equal to 2 is less than the degree of the denominator, which is equal to 4. Okay, so it means the 2 conditions are satisfied. So next we're going to use exactly what the partial fractions expansion says. Okay, up to here. All right. This one. All right, so this is question number 3, the function we also integrate. And when you guys use the partial fractions method at the beginning, first step, you need to factorize the denominator. And I realize here, from these 2 terms, you guys can see x cubed is a common factor. And when I factor out x cubed, so I'll get x plus 1 here. And from these two terms, the third and the fourth one, you guys can see x is a common factor. So you factor out x, you will get just x plus 1. And from this step, you guys can see x plus 1 is a common factor. We're gonna take it out. And when you do so, in the first term, it remains x cubed. And in the second term, it remains x. And we need to factorize again this, because in the first step, the partial fractions decomposition says you factorize the denominator until you get linear factors and irreducible quadratic factors. So this is not linear, it's a cubic factor. So that's why I'm going to take x out from the second bracket. If you take one x out, it becomes only x squared plus 1. And the x that I took from this is right here. This x is from the second bracket. And now I have one linear factor, which is not repeated, a second linear factor, not repeated too. And the last factor is a quadratic factor, and it's irreducible because we cannot simplify it. And now we're ready to get the partial fractions decomposition. And for the linear factors, we have these two terms. From the quadratic factor, we have the third term based on the third step of the partial fraction decomposition method. So next step, we have to find A, B, D, and E, and then calculate the integral. I'm gonna let you write down the solution here. After we'll see how to find A, B, D, and E. Is it okay up to here? So you guys are done?
Yes, sir.
All right. So next, I'm gonna find A, B, D, and E by using, the same technique that we use for example 1 and 2. All right. And to get the common denominator, so you guys have to multiply this first term with the second, with x plus 1 and x squared plus 1. You multiply them with up and down. And here for the second term, you multiply x and x squared plus 1 up and down here. And for the last term, you multiply up and down by x times x plus 1. Okay, so that's what I did here. So one here. Is it okay? So one. move it like that. It's supposed to be a 1 here because it's just this x plus 1. It's a typo. Okay. Now I'm going to expand this numerator, so we'll get exactly this. So you have ax cubed plus ax squared plus ax and plus a. And for the second here, you will get second term, you will get bx cubed plus bx. For the third term, so you expand this part first and you multiply with this, it's going to be dx cubed plus ex squared plus dx squared and plus ex. And as I did before, I'm just going to keep all a coefficient of x cubed first together. So we have x cubed here. The first coefficient is a for x cubed. For the second one, we have b x cubed and dx cubed. Going to give us the first term here. And for the x squared, you have a, the coefficients, and the next one is here e plus d. That's what we got here. And for the coefficient of x, you guys have a here, b, and e. And for the constant without x, we only have a, this term, the only term where you guys don't have ax. Now we have to compare the two numerators, this numerator here and this one. Equal to this numerator. Because the denominators are the same. Okay, so you compare the numerators because you guys have the same denominators. Now, the numerator from the left does not contain any x cubed. So it means the coefficient of x cubed from the left is 0. So that's why this coefficient should be 0, the coefficient of x cubed. And the coefficient of x squared from the right is a plus e plus d, and the coefficient of x squared here from the right is 1. So that's why we got here a plus e plus d equal to 1. So the coefficient of x here is a plus b plus e, and here the coefficient of x is equal to 3. And the constant a is equal to -1. And that's what I gives you. So you compare the two numerators. So this is equal to 0. This one should be equal to the coefficient of x squared from the right, from the left is 1. And coefficient of x here should be equal to coefficient of x here, which is equal to 3. And the last term here should be equal to this last term. And knowing the value of a, I'm going to substitute in these three equations a by -1. Okay? From the first equation here, if you substitute x by -1 and you send it to the right-hand side, it becomes +1. That's exactly what we got here. This equation here is obtained from this first equation when you replace a by -1 and you send it to the right-hand side. For equation number 2, again, you substitute here x by a by -1 and you send it here, it becomes +1. So we'll get 1 plus 1, that's why we got 2. And here you substitute a by -1 and you send it here, you're going to be 3 plus 1. That's why you got 4. Is it okay so far? Again, we have 3 equations with 3 unknowns. So now from this equation, you guys have B equal to 1 minus D. And from the second equation, so you guys have E equal to 2 minus D. And that's exactly what I wrote here. I said here star give us D equal to, so the first equation is what I call star. The second equation is double star. And the third equation is triple star. And from the first equation, I'm going to isolate my B and express in terms of D. That's what I did here. And from the second equation, I'm going to isolate my E and express it in terms of D. It's going to be 2 minus D. And in the third equation here, I'm going to substitute now B and E by their values here. So B going to be 1 minus D and E going to be 2 minus D. Now from, as I said, from star is this first equation, I have B equal to 1 minus D. From double star, I have E equal to 2 minus D. Now I'm going to substitute here. I'm going to substitute here B by its value in the third equation, the triple star. And E, I'm going to substitute again by its value here. And after doing that, we'll get this part. So this is, obtained when you substitute B and E by their values. And now the equation depends only on D. So we'll get minus 2D equal to 1, because when you drop the brackets, you will get here minus D going to be minus 2D, and we'll get 1 plus 2 going to be 3. So the 3, you send it here, it becomes 4 minus 3. That's why we got 1 here. And from this equation, you guys can see D equal to negative 1 over 2. Okay. So from this last equation, you get D equal to negative 1 over 2. And to get B, I'm going to substitute here in this equation. Here, I'm going to substitute, D by negative 1 over 2. And by doing so, the B going to be 1 minus negative 1 over 2. It becomes 1 plus 1 over 2, which is equal to 3 by 2. And in this equation here, I'm going to substitute again D by 1 over 2 is going to be 2 minus negative 1 over 2, which is equal to 2 plus 1 over 2, going to be 5 over 2. So now I know the values of A, B, E, and D. So next step, I'm going to substitute, these coefficients by their values in the partial fractions decomposition, and then we're going to integrate our function. Any question?
No, sir.
All right. Thank you. So next step, I'm gonna substitute here. I'm gonna substitute, A, B, D, and A by their values. A is equal to 1 over 2. B, I guess, was 3 over 2. C was 3 minus 1 over 2. And this was, 5 over 2. We just substitute. Okay, so when we substitute, we'll get exactly this in the integral. I substitute here A is equal to minus 1. So B is equal to 3 over 2. C is equal to negative 1 over 2. And D is equal to 5 over 2. Now we're ready to integrate this. So this is the value of A. This is the value of B. So this is D. And we have here E. And this part here, I'm just going to copy this first term. And here 3 over 2, I just bring it down here. Factor out. And this, I just took negative 1 over 2 out from the numerator here. So when you put it back, it becomes a negative 1 over 2x, and negative 1 over 2 minus 5 going to be plus 5 over 2. So in fact, this is going to be just 4 here because we did it before. When you integrate this function here, the first term is going to be 1 over 2. And with this 1 over 2, it becomes 1 over 4. And here you have 5 times 1 over x squared plus 1. But 1 over x squared plus 1 is the derivative of tan inverse. That's what we got here. And you put this 1 over 2 inside. Any question?
Excuse me, sir.
Yeah.
Yeah, I want to know how to get the tangent inverse x.
This part here?
Yeah.
Because this is a derivative of tan inverse. I just want to show you. All right, so because here is the 5, so you have a 1 over 2 out. So that's this part, okay? You have the integral of plus 1, and we have minus 5 over, I'm just doing this part here, the integral of this part. That's what I'm doing.
Okay.
Okay. So here's going to be x. Oops. Okay, we have x u squared plus 1 dx. Okay. And now I'll get here negative 1 over 2. So integral of x over square root of x, not x squared plus 1, sorry. And here I'm gonna write it as 5 times 1 over what's going on? Oh. All right, so it's gonna be here 1 plus what? X u squared.
Okay, sir, I know how to do it. Thanks.
So
Yeah, so 1 over 1 plus x squared equal to 10 inverse x.
yeah,
Okay, I got it. Thank you.
so this is a derivative of tan inverse. So this we did it previously. It's just a 1 over 2. So we'll get here negative 1 over 2. So for this antiderivative we've seen before, we did it, twice. It's just 1 over 2 ln of x squared plus 1 minus 5 times tan inverse. And that's what I did here. So now when you put this, you drop the brackets, you will get negative 1 over 2 times 1 over 2. That's why I said going to be here 4. Because you multiply these two. And then negative 1 over 2 times minus 5, it becomes a plus 5 over 2 tan inverse. And you add the constant C. Any question?
Excuse me, sir. So
yeah,
the ln of x squared plus 1 in the answer, why isn't it in modular signs?
Pardon?
So in the answer, there is ln of x plus 1, and those are in modular signs. But then the ln of x squared plus 1 isn't. Why?
Why we don't have absolute value here?
Yes.
Yeah, because this is already positive. The absolute value is going to be equal to itself here. Because if you take a number, you square it, it's positive. You add 1, it's still positive. But here, we don't know what is the sign of x. So that's why we take the absolute value. But here, it's already positive because of the square.
So if it was cubed, you would have to have the absolute.
Yeah.
Okay, thank you.
Yeah. Any other question? All right. So we're done now with the partial fractions technique. And to conclude, I'm just gonna give you here some advice about, choosing the right method when you guys have an integral, because it's not obvious to find the appropriate method quickly. And what I recommend you is when you guys have an integral and the integrand looks complicated, means you don't know exactly what is the antiderivatives, you start by trying to simplify it. And we have different ways depending on the kind of function that you guys have. So for example, when you have a function involving the square root and you want to cancel the square root, don't square your function, because if you do so, you're going to change totally your question. What you can do is inside the integral, you can multiply, for example, with the conjugate. You multiply the conjugate, on the numerator and on the denominator. If your functions, for example, involve, trig functions, you can use the trig substitution formula that we've seen, not trig substitution, but trig transformation formula that I gave you, I guess, 2 or 3 weeks ago. And I told you have to memorize them. I'm going to help you a lot. to simplify your integrand. Okay, and after doing so, it's going to be obvious to see if you can use substitution, or you can use strict substitution, or you can use, integration by parts. But most of the time, you will need first to simplify the writing of your integrand. And as I said, the integrand is just a function that you have inside your integral. Okay. So as I said here, you classify the integrand depending on the form. As I said, if it's a square root, you multiply with the conjugate. If you have a trig function, you use the transformation formula to simplify it. And if you have like a rational function, so you try to use the partial fractions decomposition in order to simplify it. Okay, so if you try something else, if you try something, and it doesn't work, you can just leave it there and try another method. But this comes with experience. You have to practice a lot, these techniques. I'm just gonna give you like some examples, and we will see different ways to manipulate. So if you guys have product of two functions, you can try to use the integration by parts. If you have a, let's say, a composite function, so you see you have inner function, you can use, for example, the substitution rule. If you realize the integrand is a composite of two functions. Right. I'm just going to give you some examples to see. So let's say this, you guys want to integrate the tan cube of x over cos cube. At the beginning, this function looks complicated because if you look at this function, you don't know, okay, so which function has its derivative equal to tan cube over cos cube? I don't know exactly what is it. So that's why you need to try to simplify it. Okay, now how to simplify, because you have different formulas and you need to know which one is going to work. But remember, you guys have seen 6 formulas, and among the 6 formulas involving the trig functions, 2 of them use tan and secant. 2 of them. Since you already have tan, you think about, okay, so how to get my secant, and try to use one of the formula. I'm just going to remind you the formula again. So we have one of them, which is equal to secant x to the power n. If you guys remember the 6 formulas, times tan. Okay, and we know this is equal to secant x to the power n over n plus the constant c. Oops, plus the constant c here. It should be n in here. You guys remember this formula? And we have a second one also using tan and secant. So we have tan to the power n, and we have here secant square. And based on the formula, this is equal to, it was, I guess, formula 3 and 4 among the 6 formulas. So it is going to be here 10x to the power n plus 1 to the power n plus 1 over n plus 1 plus the constant c. Now I'm gonna try to get one of these two formulas because my integral here involves the tan, and I already know these two formulas. And you realize here, you guys can write this integral as 1 over cosine x to the power 3 times 10, right? Because I'm trying to get one of these two formulas. And you know, 1 over cosine is equal to secant. So I can write it as, you know, this is what I told you. Try just to simplify your integrand because what you guys have here, you don't know how to integrate it. So it's going to be secant cube x times tan cube x. And now you can compare this integral and these two formulas. So you guys can tell me which one do you have? Do you have number 1 or number 2? Or none? Which one do you have?
Number 2.
Number 2. So in number 2, it should be secant square. We have secant cube here. Right? We don't have number 2 because for number 2, this should be secant square.
Excuse me, sir.
Pardon?
Sir, one of my friend is trying to enter your class. Would you be kind enough to let him in?
Okay, so you're gonna block all this, you know. So we don't have number 2 because for number 2, it means your n equal to 3, but here should be 2, should be a square as number 2. So it means it's not number 2. What about number 1? It's not, because for number 1, the tan is to the power 1, not to the power 3. So what you guys have to do from this step, knowing these two formula, you manipulate again in order to get one of them. Okay? So we have two ways to get this. I can just split this secant cube into secant square times secant, but if I do so, I will not get none of these two because I'll get my secant square, but the remaining secant, I'll get the secant square, but the remaining secant, I don't know exactly what to do with. That's why I'm gonna split the 10. So it's gonna be here integral of secant x to the power 3 times the 10 cube. I'm gonna write it as 10 square times 10. So 10 square x times 10x. And we also know secant square and this is equal to integral of secant cube of x and 10 square we know is equal to secant square minus 1. We've seen this formula like 2 or 3 weeks ago. It's one of the list that I gave you, secant square x minus 1 times 10. Now I can open the brackets, and by doing so, I'll get integral of, but secant cube times the secant square is going to be secant to the power 5. So we'll get here sec x to the power 5 times 10. Because I put this secant inside the bracket and this tan too inside the bracket. So minus secant cube x times 10. And you guys can see I have exactly number 1. I have it twice. Right? So you guys can see this is number 1 when n equal to 5. And this is number 1 when n equal to 3. So you can conclude now, if you memorize the formula, it's going to be just, secant to the power of 5. I'm just applying number 1 now over 5. I'm just applying here number 1 when n equal to 5. Minus, you applied again when n equal to 3 is going to be secant cube of x over 3 plus now the constant c, and we're done. So you guys can see we manipulate in order to get, one of the formula that we've seen, and you applied. So from here, if you don't remember the formula now, what you guys can do is use a substitution rule as I told you. So you can set, for example, u equal to secant, and you calculate your du. And when you get your solution in terms of u, you substitute back. Any question? So we just apply number 1. We apply when n equal to 5 and when n equal to 3. Any question? All right, can I erase this? Can I erase this, guys?
Excuse me, sir.
Yeah.
Can you go to the previous page for a minute, please?
Which page?
The last one.
Are you talking about this page?
Yes, sir. The continuation of this page.
The top?
No, sir. After this, the last one, sir. The last part.
This?
Example 9. I'm trying.
Pardon?
Yeah, sir. Thank you. Just a minute, sir.
Yeah, I asked you, you didn't answer, so that's why I erased it.
Thank you, sir.
You're welcome. All right, so next example. So we have 2t over t minus 3, you square it. So now what I did here, so in this case, we have for this method, for this integral, we have different methods. You guys can see this is a rational function. And so it means you can use partial fractions decomposition. I'll not use it because the partial fraction is too long. You have to find the partial fractions with the coefficients. Second step, you find the coefficients, and the third step, you calculate integral. Okay, but just keep in mind, you guys can, if you want to use it, practice at home. You can use this, use partial fractions decomposition. But in here, what I just, expand the denominator, and I got here 2t squared minus 6t plus 9 And I realize when I calculate the derivative of the denominator here, if you calculate the derivative of the denominator, it's going to be 2t minus 6, right? And now I don't have 2t minus 6, I only have 2t. And I'm trying to get what we used previously. I'm trying to get this. I'm trying to get integral of f dash over f, because I know this integral is equal to ln of f. So that's how I'm trying to get it. So since I know when you calculate this derivative here, so I'll get 2t minus 6, and it means the minus 6 is missing. So that's why I add here minus 6 and plus 6, because it's just adding 0. Minus 6 plus 6 cancel out, becomes only 2t. And the reason why I pick my 6 instead of another number is just coming from here, because I know when I calculate the derivative of all this, I'll get 2t minus 6, and the 2t is already here. Now doing so, I'm going to split it into quotients. I'll get 2t minus 6 as the numerator of the first quotient, and for the second one is going to be only 6. And now you guys can see this first term is exactly this. It's exactly this. You have f dash over f to integrate. That's exactly what you have in this case. And as the question mentioned, it's going to be just ln of absolute value of f. And for the second one, this is just exactly calculating integral of t minus 3 to the power negative 2. Right? Is this part here. So is it, and so you take the 6 out, and this we know this is just equal to it's going to be t to the minus 3 just by using power, and this becomes minus 1 over t minus 3. So that I use to get the second term, and then I multiply by 6. So we have minus sign coming from here, and plus the constant c done. Okay, instead of using this method, when I manipulate, just use algebraic technique. You guys can use integrate. You can use as I mentioned at the beginning. You can use the partial fractions decomposition, or you can use the substitution rule. You can substitute here by sitting at the beginning u equal to t minus 3, and you will get the same solution too. Okay, so in this case, we have 3 methods to solve the same problem. But the substitution rule or this technique are faster, are faster than using the partial fractions. Any question? All right, third example. If you guys don't have question, I'm gonna erase this. And for the third example, we have integral of root of 1 minus t times, over 1 plus t. So this looks complicated with this because of the square root, And as I said, I'm gonna repeat it again, don't square this function because you cannot go inside and square it. If you do so, you're gonna change your initial integral. I've seen in past, semesters, people squaring this, and after when they get the solution, they take the square root of the solution. It's not the same thing. So be careful, okay? And what you guys have to do in this case is just to manipulate in order to, simplify this writing. And what I do in this case, I'm gonna just multiply with 1. I just wanna multiply with 1. And the right one that they use, because if you multiply with 1, you don't change anything. So what I did here is just as I said, you multiply with 1. When you multiply by 1, you have square root of, because under the square root, this is only 1. 1 plus t over 1 plus t is 1. So it means you have root of 1, but root of 1 you multiply with this, you don't change anything because you just multiply with 1. And now I'm gonna write it as 1 single square root. Sorry. So when I wrote it, as just 1 single square root, I'm gonna multiply the 2 numerators and the 2 denominators under the square root. And it becomes square root of the numerator over the square root of the denominator. But the square root of the denominator is also a square. So the square root gonna cancel this square. It becomes only 1 plus t. And the numerator is a, has a form a minus b times a plus b. And you guys know this is just the difference of two squares. It's gonna be just a square minus b square. When you calculate this, it's gonna be 1 minus t squared. And under the square root, you guys have the difference of two squares. And we've seen it last week. Anytime you guys have under the square root the difference of two squares, you can use the trig substitution. In this case, we have here this situation, square root of a, we square it, minus b squared over x squared. And last week, we've seen in this situation, your substitution formula going to be x equal to a over b sine of theta. And this is the situation that we have. But in our example here, a is equal to 1, b is equal to 1, and the x is t. So the t stands for x. So it means your t going to be 1 over 1 sine of theta. Okay? Because of what I said, you can set here t equal to t equal to 1, because a is 1, b is 1. It's going to be 1 over 1 sine of theta. Okay? And in this case, your dt gonna be derivative of sine. When you differentiate sine, you'll get cosine of theta, d theta. And now when you substitute here, it's gonna be integral of square root of 1 minus sine squared theta. You substitute t by sine theta and you square it. Okay, over, and the denominator is going to be 1 plus sine theta. And the dt is going to be cosine theta d theta. Is your dt. Is it okay? Any question? All good? So you guys can see here at the beginning, this manipulation that we use to simplify our function, and then you can see after that you have the difference of 2 square under the square root, and as I told you, in this situation you guys have to use the trig substitution. Okay. So by doing so, the integral becomes now. That's what I did here when I substitute. And under the square root here, 1 minus sine square, we know is equal to cosine square. The reason is we've seen cosine square plus sine square is equal to 1. So that's why 1 minus sine square is going to be cosine square. And the square root of cosine square is going to be cosine. Now I'm going to multiply these two cosine theta. So I'll get cosine square theta over the same denominator. Okay. And cosine square, as we know, you already use it here, is 1 minus sine square. We can write as 1 minus sine square. And this is the difference of 2 square. We have going to be 1 square minus sine square, going to be just a square minus b square. And we know this is equal to a minus b times a plus b. It's going to be just 1 minus sine theta times 1 plus sine theta. And you guys can simplify here. Okay. So from this step, I'm going to simplify 1 plus cosine theta. So I'm going to simplify here 1 plus cosine theta and 1 plus cosine theta. See, here is supposed to be minus now. And the integral becomes integral of 1 minus sine theta, and quite easy now to integrate it. It's going to be just theta plus, but minus sine theta is the derivative of cosine theta, and plus the constant c. Now to conclude, we're going to use the back substitution. But at the beginning, you guys can see here, I'm going to isolate my theta. So I have here t is equal to sine theta. So it means sine inverse of t going to be theta. Is okay. So now we can substitute theta by its value. But for cosine, I'm going to use the substitution here with the right triangle here. So here is theta. But you guys can see from here, sine theta is equal to opposite side over the hypotenuse. So here's the hypotenuse going to be 1 because it's a t over 1. So it means the numerator here t is the opposite side, and the hypotenuse is equal to 1. And the adjacent side, by using Pythagoras theorem, going to be 1 u squared minus t squared. And from the triangle here, the cosine of theta going to be adjacent side over the hypotenuse. So hypotenuse is just 1. It's going to be just adjacent side. So knowing the value of theta and the value of cosine theta in terms of t, to conclude the last step, we substitute back. is going to be here, sine inverse of t. Plus now, cosine, we already calculate here, is going to be square root of 1 minus t squared. And plus the constant c. Any done? And don't forget the back substitution. Any question? So do you guys have any question?
No, sir.
All right. If there is no question, I'm just gonna take the attendance before letting you go. That's all for today. And in our next class next week, we're gonna introduce a new kind of integral called improper integral. Can I erase this? So you guys are done with this page, the solution here? Okay, you can tell me before I erase it. Hello? Okay, I'm gonna erase it.
Just 1 second, sir. Oh,
No, 1 second, you're kidding me?
sorry. Sorry.
Yeah, I already erased it. I asked you many times. You didn't say anything.
My bad.
Okay, I'm gonna take the attendance before letting you go.